So today, and I thought I changed this, what I would like to do today is look at some of the basic calculations that we will need to do throughout the semester. So these will provide essentially a grounding for the material or the calculations that we will do throughout the semester. So the first thing is just a quick review, some basics. So when we talk about stoichiometry, it's that part of chemistry that's concerned with measuring the proportions of elements or compounds involved in a reaction. So we always talk about reactants, we talk about what's formed, the products, and the stoichiometry gives us that quantitative information about the number of moles of reactants that react to form X moles of products. So when we look at balancing equations, we need to think of both balancing the element on either side of the equation. And if we're looking at redox reactions, then we need to look at balancing the number of electrons that are transferred. So for example, and we'll use this reaction in an example, if we have octane reacting with oxygen by perfect combustion to form CO2 and water, we can balance this reaction. We have 8 carbons in the left-hand side in our product, so we need 8 carbons on the right-hand side. We have 18 hydrogens, so we need 18 hydrogens on the product side, so we'll multiply that by 9 so that we have 18. And now we can look at the number of oxygens. It's easiest if you have something like oxygen that's a single, it's a molecule, but it's made up of one single element. It's best to just leave that to the last. So we have 16 oxygens here. We have 9, so we have 25. So we need 12.5 moles of oxygen. So for every 1 mole of octane, 12.5 moles of oxygen will react to form 8 moles of carbon dioxide and 9 moles of water. It's a little more complicated if we look at the redox chemistry. So for instance, if we look at rust reactions, so we start with metallic iron, reacts with oxygen, and forms Fe2O3. So we start with iron that has an oxidation state of 0, and in ferric oxide, the iron will be 3 plus, our oxygen's 2 minus. So this goes to Fe3 plus, but we have 2. So go from Fe0 to Fe3 plus, we need 2 moles of iron on the product side. And we're going from 0 here to 3 plus, but we have 2 iron. So we need 6 electrons. We need to balance the charge. We need to balance both charge, and we'll look at balancing electrons. With oxygen, we have O2 going to we have 3 oxygen. Each oxygen is 2 minus, so we have a total of 6 minus, but we need 2 oxygens, and now we've got 6 oxygen atoms, so we need to multiply that by 3. Now we need to look at charge. We have 2 minus for each oxygen, but we have 3 here. And now we've multiplied that by 2, so we actually have 6. So we have 2 times 3 here, times 2, 12. So we've got 12 electrons being transferred. So now we've got 6 electrons transferred in the first half reaction, 12 electrons transferred in the second half reaction. So we need to multiply that first half reaction by 2. Now we'd have 12 electrons transferred in the oxidation reaction, 12 electrons transferred in the reduction reaction. We can add those 2 together. And that, now we have 4 plus 3 oxygen goes to, we've multiplied this whole reaction by 2. So we have 2 Fe 2O3. So we've got 4 ions on both sides. We have 6 oxygens on both sides. And in these 2 half reactions, we've transferred a total of 12 electrons. We don't write the 12 electrons because they cancel in the reaction. Any questions? Just a quick review of stoichiometry. Let's look at using that stoichiometry. So in a normal year, when I would drive to campus, it's about 10.6 miles back and forth from my house to work, to the engineering building. And if I have a car that gets 30 miles per gallon, I want to know how many kilograms of CO2 are emitted during my daily commute. We're going to represent gasoline as octane. So this is octane. We've just written the balanced equation. In this case, I've multiplied the entire equation by 2 so that I don't have any fractional amounts. And the density of gasoline is about 0.75 kilograms per liter. Let's just write out the information that we have. So I travel 10.6 miles per day, although right now I travel pretty much 0 miles per day, but in a normal year, get 30 miles per gallon. That means I am consuming in the car 0.35 gallons of gasoline per day. 0.35 gallons per day times 3.785 liters per gallon means that I'm consuming about 1.3 liters of gasoline per day. I need this on a mass basis, so I'll multiply it by the density. So I have 1.325 liters. And this is really liters per day, times 0.75 kilograms per liter, and that is 0.994 kilograms per day. So that's, on a mass basis, that is the mass of gasoline that I'm consuming per day. I need the molecular weights of, I'll need it for octane. I'll also need it for CO2. So for octane, the molecular weight is 12.01. And I'm going to use kilograms per kilomole here. Typically, we use grams per mole, and it's really a gram mole, but we rarely write gram mole. But because I've used kilograms, I'm just going to use kilograms per kilomole. We'll multiply this by 8 plus 1.008. Again, kilograms per kilomole. This is the atomic weight of hydrogen times 18, and that is 114.2 kilograms per kilomole. Okay. So we had 0.994 kilograms per day. We'll divide that by 114.2 kilograms per kilomole, and that is equal to 0.0087 kilomoles per day. And I apologize for the lines. I was hoping that being hardwired to the network would solve that line problem. It's not. So I'm not sure how to eliminate it. Those of you that have had NAFL 483 in the fall know this was a typical problem. Like I said, I thought maybe being hardwired would work, but it's not. So we have kilomoles per day. This is kilomoles of octane. We will consume, go back to this reaction here, 16 moles of CO2 for every 2 moles of octane, or 8 moles of CO2 for every 1 mole of octane. So we have 8 kilomoles of CO2 that we produce for every kilomole of octane that we burn. And we'll multiply that by the molecular weight of CO2, and this is kilograms per kilomole, and that is 3.06 kilograms per day of CO2. So roughly, I'm producing on a mass basis 3 times more CO2 than I'm actually burning. So this is what I've combusted, and this is what I'm producing. So you can see it's quite significant. It's one of the reasons why there's questions whether or not we need, or debates whether or not we need to move from the internal combustion engine to electric vehicles because of the amount of CO2 that is produced. You can see it's significant. Any questions about this example? Yes, no? Okay. In looking at air pollution, we will use the ideal gas law extensively. So pressure times volume is equal to the number of moles times the ideal gas constant times the temperature. Temperature is always in Kelvin. And then we can also use both the combination of Charles' law and Boyle's law that says that the volume in condition 1 times the pressure at that condition divided by the temperature is equal to the volume at condition 2 times the pressure at condition 2 divided by the temperature at that condition. Again, temperatures need to be in Kelvin. The other law that we will use is Dalton's law of partial pressures, and that just simply says that the partial pressure of each of the gases summed equals the total pressure. So for example, room that I'm sitting in here has what major gases? The room that you're sitting in has what major gases?
Oxygen and nitrogen.
Okay, so we have oxygen. We have nitrogen. What else?
Probably some CO2.
CO2.
Definitely some CO2. Anything else?
Water vapor.
Water vapor. Those are the major gases. Hopefully there isn't much in the way of carbon monoxide. Hopefully there isn't much in the way of volatile organic chemicals, but those are the major ones. A little bit of argon, but like I said, those are the major ones. And this is equal to the total pressure. So assuming that we have no other gases present, if I add up the partial pressure of each of those gases, that equals the total pressure. So we can do a problem like this. In this case, you're told that you have 28 liters of a gas. So let's say we have some sort of a storage drum. Okay. And we have, let's say we have some liquid at the bottom. But we measure the gas, and we find that we have some methane, we have nitrogen, and we have CO2. So that's what's in here. And you're actually told the masses of each. This volume is 28.0 liters, and the temperature is 300 degrees Kelvin. And you're asked to determine the partial pressure of each of the gases in the container along with the total pressure. So in order to do that, what approach should we take? Or what of those previous laws that I gave you will we use? So what do we have? We're looking for pressure. We have volume. We have temperature.
Wouldn't it be Dalton's law?
We will need Dalton's law. Okay. But in order to use Dalton's law, we need the partial pressure of each of the gases. So in order to determine the partial pressure of each of the gases, what law will we use?
Ideal gas law.
The ideal gas law. So we can, since we're given the mass, we can determine the number of moles. We're given volume, we're given temperature, and we can determine by PV equals nRT, we can determine the partial pressure of each of these gases. So we'll do exactly that. We have 11 grams of methane. We have 1.5 grams of nitrogen. We have 16 grams of CO2. So we'll divide each of the masses by the molecular weight. And in this case, we can use grams per mole or grams per gram mole. And this is equal to 0.6857 moles. We'll do the same for nitrogen. Divide that by the molecular weight of nitrogen. And that is equal to 0.0536 moles. And we have 16.00 grams of CO2. We'll divide that by the molecular weight. It's 44 grams per mole. And that is 0.3636 moles. Okay. So to get the partial pressure of methane, we'll use PV equals nRT. So we have 0.6857 moles times 0.082 atmospheres, liters, moles, degree Kelvin. You'll find that I prefer using that set of units for the ideal gas law. That is equal to, or times the temperature and divided by the volume. So temperature cancels, volume cancels, moles cancel, and I'm left with units of atmospheres. So this is 0.6024 atmospheres. And I can convert that to kilopascals if I wish. And there are, just write it over here. 1 atmosphere is equal to 101.325 kilopascals. Do the same for nitrogen. Just trying to figure out what happened to the oh, there's the transcript. And that is equal to 0.0471 atmospheres, or 4.77 kilopascals. Same for CO2. I'm not going to write out the whole equation, but this is 0.319 atmospheres, or 32.4 kilopascals. So the total pressure is equal to P methane plus P partial pressure of nitrogen plus the partial pressure of CO2. So it's equal to 0.6024 plus 0.0471 plus 0.319, and that is equal to 0.969 atmospheres, or 98.2 kilopascals. So that would give us the partial pressure, or sorry, the total pressure in this drum. Now there's a lot of problems. The homework is very much aligned with these problems, but I want to make sure that you've got a good foundation to move forward.
I had a quick question.
Sure.
Did you use that version of R just based on what was given in the problem, pretty much?
Pretty much. My undergraduate degree is actually biochemistry, and that was the version of R that we always used in chemistry. It's the version that I'm actually most comfortable with. So you will tend to find that I will use that version of the ideal gas constant and do the conversions later. You don't have to. You could, you can do the conversions otherwise, but I just find that one easier. And it's really a matter of preference.
Okay, thanks.
I want to take this concept one step further. And it's not uncommon that, in fact, it's actually very, very common, that where you have some sort of an industrial source, be it whether it is the exhaust pipe from a large bakery to the smokestack from the power plant, that we have to measure the concentrations of a variety of pollutants in the stack gas. We often we may take samples from that stack gas, take it back to the lab. We may monitor it and determine it there. We may measure it on site. But in this case, we have a situation where we've measured the concentration of SO2 in the stack gas to be 90 milligrams per cubic meter. Typically, with air, you will find that we will rarely use liters as the volumetric unit. We will typically use meters cubed because our concentrations are significantly lower. In water, we use milligrams per liter. So water is more dense than air. Air, we typically will use cubic meters, or we'll use parts per million by volume. So we have stack gas, and it's emitted at a flow rate of 8 cubic meters per second. That's what we measure. The temperature of the stack gas is 220 degrees C, and the pressure is 120 kilopascal. The flow meter that we used to measure this flow rate was calibrated at 20 degrees C and a pressure of 101.325 kilopascal, so 1 atmosphere. We're going to calibrate this at ambient temperatures. We're not going to want to calibrate it under pressure. We're not going to want to calibrate it under high temperature. We calibrate it typically at room temperature. You're asked then to determine the mass of SO2 that's emitted per day. The first thing we need to do in order to do this is this flow rate here, okay, of 8 meters cubed per second. As I said, okay, that was measured with an instrument that was calibrated at a different temperature and pressure than what was used to measure that flow. So we need to do a correction to deal with that difference in temperature and pressure. So let's look here. We have a concentration of SO2 of 90 milligrams per cubic meter. This Q that we determined, this is the Q that was determined in the stack, but at the calibration conditions, because the instrument doesn't know the temperature and the pressure, unless it has some sort of internal mechanism in there to measure both and do an internal correction. If it doesn't, and it's a very simple flow meter, it doesn't, okay? So this Q is really the Q determined based on the calibration condition. The temperature at calibration is 20 degrees C, and the pressure at calibration is 101.325 kilopascals. What we want to know is what is the true flow rate, or what is the actual flow rate in that stack. And the temperature of the stack is 220 degrees C. The pressure in the stack is 120 kilopascals. So we can use the combination of Charles' law and Dalton's law where we have V calibrate times the pressure at the calibration divided by the temperature for that calibration is equal to V stack times P stack divided by T stack. Okay? So we have two different sets of conditions. Given that, what we really have is a volumetric flow rate. So this should be kilograms per second. Okay, it's in a volume. So instead of Q, we'll use a volumetric flow rate. So we have the volumetric flow rate in 8 cubic meters per second times the pressure divided by the temperature, and we need to convert to Kelvin, and that is equal to this, it's really, in this case, Q stack. It's our volume per time, times the pressure divided by the temperature. So Q in the stack is equal to 11.37 cubic meters per second. Does that make sense?
I'm not sure how you got from V to Q there.
So Q is just V over time. So
Okay.
Okay, so I just substituted in, instead of using, since we have a volumetric flow rate, I just substituted in Q. Basically ignoring the fact that it's per time. And I can only do that because I have a volumetric flow rate. If I had a mass flow rate, I couldn't do that. So now what I want to know is, what I was asked was the mass of SO2 emitted per day. So now I'm asked for a mass flow rate, and we'll use m dot for mass rate, and that is equal to this true stack, sorry, the true flow rate in the stack times the concentration that we're given. And that is equal to 11.37 meters cubed per second times the 90 milligrams per cubic meter, and that is 1,023 milligrams per second. So what I've calculated here, and I apologize for all the extra lines. So I've now calculated the mass of SO2 that's emitted per day. And in terms of regulations, that power plant is regulated on a mass basis. The mass of material, whatever chemical we're looking at, emitted per day. Questions? Why is Q stack not V dot? I could have, the question is why did I use Q stack, not V dot? I could use V dot and make it a volumetric rate. Q is defined here. It's equal to, do it this way, the volume per time. So I've simply substituted in, instead of using volume here, I've used Q, or Q per time. Please feel free to ask questions. The last part of the review that I think we'll get to today is looking at the transfer of gases. We will look at this in a number, especially the unit processes, and treatment of gases towards the third part of the semester. But it's also relevant. It's relevant when we talk about acid rain. It's relevant when we talk about climate change and CO2 emissions. So when we look at CO2, we have CO2 in the gas phase, and we can kind of think about this in terms of droplet of rain. So we have CO2 in the gas phase. That CO2 can dissolve into the raindrop. So now we have aqueous CO2. That aqueous CO2 reacts with water to form carbonic acid. Similarly, we can have ammonia in an aqueous phase, and that ammonia can be in equilibrium. Really, these are all equilibrium reactions. That ammonia, aqueous ammonia, can be in equilibrium with the gas phase ammonia. So we can write these as equilibrium expressions, and we'll use Henry's law. And Henry's law simply states that the concentration in the aqueous phase is linearly proportional to the concentration in the gas phase. And the factor that we use to relate those two is simply Henry's constant. Now, if we have the partial pressure in atmospheres and the aqueous concentration in molar units, then this Henry's constant will be in moles per liter per atmosphere. One of the things you need to be very careful with Henry's law, constants or Henry's constants are the units. This is really an empirical expression. You can have units of Henry's constants in atmospheres per inverse mole liter per liter. You can have it in milligrams per cubic meter, per milligram per cubic meter. There's a whole variety of units, and you need to know the units in order to use the Henry's constant. So be very careful when using Henry's constants now or in the future. If you don't know the units, don't use it. Make sure you know those units before you use it. So let's look at a problem where we have to use this information. So we have here the concentration of CO2, and this was measured a week or so ago at Mauna Loa in Hawaii, which is where we do much of the measurements of CO2 because it's out in the middle of the Pacific. And it was measured to be 415.1 parts per million. This here is parts per million on a volume basis. Typically, that's what we will use in atmospheric processes and air pollution, etc. The Henry's constant for the dissolution of carbon dioxide into water is 3.4 times 10 to the 2 moles per atmosphere at 20 degrees. And you're asked, what is the concentration of carbon dioxide in the water, assuming we're at equilibrium? And then we can ask, what is the pH? So to find the concentration, we're told that the concentration of CO2 is 415.1 parts per million. That is equivalent to 415.1 volumetric units per 10 to the 6 volumetric units. Because of the relationship between volume and pressure, that means that the pressure of CO2 is also equal to 415 per 10 to the 6 atmospheres, 10 to the 6. So that is equal to 0.0004151 atmospheres. Okay. So that's the partial pressure of CO2 in the atmosphere. 4.14 times 10 to the minus 4 atmospheres. So the concentration of H2CO3, we actually often denote it with an asterisk, and that's because this is both dissolved CO2 and actual carbonic acid, and those two, it's impossible to distinguish those two, so we essentially combine them together. And this is equal to KH times the partial pressure, and that is 3.4 times 10 to the minus 2 moles per atmosphere. You can multiply then by the partial pressure, and that is equal to 1.4113 times 10 to the minus 5 molar. So that's the concentration of carbonic acid in water. Now to determine the pH, H2CO3 star dissociates to release a proton and form bicarbonate. bicarbonate. So we can write an equilibrium expression, products over reactants, and that equals 10 to the minus 6.35. That's the equilibrium constant. It's based on thermodynamics. You can find that, for instance, in tables. We're going to make an assumption that there's nothing else in the solution other than pure water and the CO2, so that if this dissociates, the concentration of H plus is equal to the concentration of bicarbonate. If that's the case, we can substitute. So this is equal to H plus squared. We've calculated the concentration of carbonic acid, and we can solve for H plus. And that is equal to 2.51 times 10 to the minus 6, and the units will always be molar if you're looking at an equilibrium reaction like this. Now to calculate pH, that is the negative log of the hydrogen ion concentration. So that is equal to 5.60. The natural pH of rainfall is actually not 7, it's not neutral, it's actually acidic, and it's 5.6. And the pH is decreasing with time as the concentration of CO2 in the atmosphere increases. So that's a quick review of the basic equations, basic chemistry that we'll use throughout the semester. If you need additional reviews, if you go to the Reading Reflection week folder, there's a chapter 2 from a textbook. It's actually one that I co-authored with a retired faculty member, Dr. Davis. Chapter 2 reviews much of this, so if you need an additional review beyond what we just did today, that has quite a bit of information in there, and hopefully that should assist with all the homework. Any questions? We'll stop there, and then we'll continue some more of these reactions on Friday. I know it's a lot of information, a lot of review, but hopefully it'll help throughout the semester.